Hello and welcome to tutorial number 4 for the GNSS software defined radio toolbox for MATLAB version 2.06. So continuing on, we were talking about this state transition matrix for CA code. In the previous tutorial we went through all of the details of what this state transition matrix does and how it's configured. So in this tutorial, what we'll do is interrupt this transition process and have a look at the individual states and see what the tracking loops are doing in those particular states. So the first thing we want to do is look at this acquisition parameter loading and the pull-in process in state number 1. So what we're going to do is disable state number 1 from transitioning to state number 2 by setting this k value to infinity. And remember, we are doing this all in the copy and not in the original one, which we did 2 tutorials ago. So we go back to our tracking program and we set up the file, the path, the start block. The number of blocks is reduced to 3 seconds because we only want to see that first state. We are using this user call function that is the default for the distribution, and we are using this run set file. And in the channel setup, we are using CA code as the definition string, PRN17, stream 1, and this temporary run set that we are going to be modifying. So let's go ahead and run this. Alright, and we are going to plot that output, and as I showed in the first tutorial, we are going to set it so that it's going to always pull the latest tracking run for this file and plot that. So let's go and plot. Okay, so as you can see, the state transitions are just only one. So it's basically didn't transition to anything other than the initial state of 1. So now if you look at the I's and Q's, you see that we should have 5 sets of correlator outputs. So these are the wideband correlators, which are the 1 millisecond integrated correlators that are coming from the correlation engine in the C library. But if you look closely, you can see that the early 2 and the late 2 are actually disabled. So they are not running because the reason is we don't want to perform correlations that we are not going to use. So those 2 correlators will only come on when the code discriminator is set to a double delta, which is going to use those 2 side correlator values. But anyway, you can see that because it's FLL, that the I's and Q's are rolling around, right? So the phasor, which would be A tan 2 Q over I, is actually rolling around, and that's what frequency lock loop essentially means. If I zoom in here, you can see that the the prompt correlator is at the top, and then the early and late are below that. So this is the one chip correlator spacing that we implemented in that first state. And an FLL mode continues to happen for the duration of the run. So this one is showing you the two-quadrant arc tangent for the hardware correlators, and as we expect, the phasor is just wrapping around. This is the output of the carrier loop filter. So you can see that in the beginning the velocity integrator is set up based on the Doppler frequency offset that we got from acquisition, but you can see that it's not perfect. So it was initialized to somewhere around 190 meters. So that would translate to 190 meters per second of Doppler. But that was the approximate value from acquisition. So the velocity integrator actually had to settle to the more accurate value that it found, right? So that process took about 0.05 seconds or so, or yeah, which is 50 milliseconds or so to settle to that steady state value. And you can see that because we are running a second order loop, the acceleration integrator is not in play, so it's set at 0. This is the code filter. So because we are doing carrier aiding, there's no velocity and acceleration states. It's only showing you the range state. So as a result, you see the uninitialized pseudo range and carrier accumulated Doppler measurements. And so code minus carrier. And this is our phase locked indicator. So as I was talking about in the previous tutorial, the phase lock indicator is bouncing around between 1 and -1 because we have not reached phase lock condition. So because it's a frequency lock loop, it's moving around. Okay, so this is the pre-detection integrated correlator outputs. So it's essentially whatever pre-detection that we had in our acquisition is what's been implemented over here. Okay, so this one is the pre-detection integrated correlator magnitudes. So this is going to be interesting because it's going to show us the settling time for the code tracking loop. So you can see here that actually let's look at figure number 13, which is the post-detection integration correlator outputs. And here if we zoom in, we can see the time it took for the DLL to lock. Okay, so we can see that it takes, it goes through this these dips because of the data bit transitions. Let's have a look at so this is a much better so figure number 3 was the coherent, and because we are running on a FLL, you have these dips actually. So in figure 14 we have the non-coherent, which is a better indicator. So here we can see that it took less than 4 milliseconds for the code tracking loop to converge and find the balance between the early and the late. All right, so now let's set up a different let's extend that run. And so we had 500. So we are going to now allow it to transition, allow it to coast, and find the if there's any code carrier divergence, fix that, do the 20 data bit transition based bit synchronization, and then the transition to the phase lock mode, and go to this third order tracking loop. So let's interrupt over here and run this for about 10 seconds or so. Okay, so let's plot. All right, so now we see that we have gone from state number 1 to state number 7. And so in the hardware I's and Q's, you can see that it goes from FLL mode, where the I's and Q's are rolling around, to the phase lock condition. And also you will see here that we do go to third order. So you can see, if we zoom into the acceleration state, that in the beginning it's second order, so it's set to 2, but then when we switch on the third order mode, now the acceleration integrator is actually estimating acceleration of the dynamics, the acceleration component of the line of sight dynamics. So here there's essentially very benign dynamics, and so there's no bias in this waveform over here. So if there was a significant acceleration, this would be non-zero mean. Okay, so what's interesting here is, here you can see the phase lock indicator, and you see that somewhere near 3 seconds it transitions over to this phase lock loop mode. So we can see by looking at the states that the transition state was state number 1, 2, 3, 4, 5. So when we go back here to state number 5, we know that that transition happened. So remember, there was a 500 millisecond timeout, and then we had a transition based on that phase lock indicator. So that's happened around 3 seconds. And so you can see here that this is the the timeout, and then somewhere over here it reached the point, the indicator went to above 0.9, so that's probably somewhere over here, and then as a result it snaps to a phase lock loop. It basically turns off the frequency lock loop discriminator, and as a result there's very little that the tracking loop has to do to correct itself to go to a phase lock loop mode. And then you can see here that, so these are the pre-detection integrated correlator outputs, and we can see here that the integration time has not changed because this envelope value is the same, but you do see that we go from FLL over here, and I think over here is where we do the coasting for a second, because you can see that it's just stationary, and then eventually we go to phase lock loop, and then we also change the correlator spacing from 1 chip to 0.5 chips. So over here we can see clearly how the early late correlator outputs snap from 1 chip spacing to 0.5 chip spacing. Okay. Alright, so next we are going to interrupt at the point where we go from 2 milliseconds pre-detection integration to 5 milliseconds. So we run this and plot. Okay, so you see that over here we go to a coherent delay lock loop, and then eventually to the high resolution correlator. And so correspondingly, if we go to our plots, we can now see that over here we turn on the early 2 and late 2 correlators, and you can see that it's at I believe we have 0.25 on the inner and then 0.5 on the outer spacing. Same thing here. Now the pre-detection integration was 2 milliseconds just before. It was 2 milliseconds when we enabled the high resolution correlator, and then half a second later we went to a 5 millisecond integration. And so you can see now that the in-phase correlator magnitudes have grown by a factor of 2.5, right? Okay. And you see that here as well. So these are the coherent correlators that are used to actually form the delay lock loop discriminator. So over here we should be able to see, yeah, so this is the code discriminator, and so you can see here that it's pretty noisy, and then when we go to the coherent, which was this part here, yeah, I believe this was coherent and then this was the high resolution. So from about 3 seconds to 4 seconds and then 4.5 seconds and then 5 seconds. So let's look at those intervals. So here is where it went from non-coherent to coherent. And so you can see that there's noticeably less noise. And here we go to HRC, where you have even less noise than the coherent early minus late. And then finally, this is from here to here is where we had HRC with 5 millisecond coherent integration. So you can see that the noise is significantly reduced over here. So all this leads to lower code measurement noise and multipath rejection as well. Okay, so now let's run it through to the end, where we go from 5 milliseconds to 10, 20 millisecond integration time pre-detection, and then through that process we are also going to narrow the correlator spacing from 0.5 to 0.25 and then 0.1 and 0.01, and also somewhere in here we are going to go to a 200 millisecond code discriminator update rate to the code tracking loop. And then also we're going to run this last piece for 2 seconds and then reset the measurements. So we'll increase the runtime to about 30 seconds to make sure that we have gone through all of those states, and run this. Okay, and we'll plot. Alright, so looking at the pre-detection, yeah, looks like we didn't run this far enough. Okay, sorry about that. So what happened was I had not saved my run set file after making changes. So now you can see that the states go all the way up to 14, which is the entire state transition matrix. So you can see here the wideband correlators, and you can see here that in the last state the measurements were reset. So let's come back to figure 7 in a little bit, but let's look at this PDI integrated correlator outputs. So you can see here that we went from 2 millisecond integration to 5 millisecond to 10 millisecond, and then all the way up to 20 milliseconds. And then at 20 milliseconds we had over here we started off with 0.25 chip spacing, and we went to 0.1 and then 0.01. So you can see here correspondingly that we started with that 0.25 2.5 over here, and then over here we go to 0.1 chip right around here, and then over here we make the transition to 0.01 chip correlator spacing. So if I zoom in here, you can see that 0.1 to 0.01, and at 0.01 the spacing is so close that you can hardly see a difference. But even though it's right at the very top, all those 5 points, there's still the correlation function is very flat, but still there's a maxima that it can resolve, and hence steer the code discriminate in the right direction. So you can see here in figure number 16 that, so this was the noisy 1 chip, 0.5 chip, and we went to coherent and then coherent double delta. But then right around here is where we start to change the correlator spacing. And you can see at 0.01 chip, the error on the code discriminant is down to something like 2 centimeters of error standard deviation. And that's what gives this incredibly low code noise. Now the only reason this works is because we are performing carrier aiding. So all of the dynamics, there's benign dynamics to begin with because this is a stationary receiver. But even those benign dynamics are tracked by the precise phase lock loop, and as a result you are giving a very clean dynamics estimate to the code tracking loop. And so as a result you're tracking most of the dynamics by using carrier aiding, and all the code loop has to do is find that slight code carrier divergence, which in this case is mainly due to noise and multipath. But when you go to 0.01 chips, there's hardly any noise because the noise is correlated between the samples. And as a result, what you're really tracking is the very slight amount of divergence that may be due to multipath. And so that's why you see this code carrier divergence. And here you can see the noise is extremely low. It's in the centimeter range. And this variation here is due to a short delay multipath. Okay, so that pretty much covers the design and configuration of the state transition matrices. Now I didn't cover a few states that are not used in this CA code example. So things like synchronization to the secondary codes. So those I will talk about in the next tutorials, where I will be discussing L2C tracking and L5 as well as Galileo E1. Okay, so thanks for listening and see you next time.